Howdy doody, everybody. So, I'm Ross from Moffenzeef Modular. Currently, I'm living in Portland, Oregon, where all of our stuff gets designed and manufactured. I do all the design work at home, and our manufacturing gets done at Dark Place Manufacturing, which is a place down the street from my house, where I used to work for a little bit. That place also does LZX and Moleco and VSL and some other places. So it's pretty cool because you can kind of just like pop in and there's someone from some synth company hanging out, and it's pretty sweet. If you guys don't know about what's happening in Portland right now, there's like totally a scene there, which is pretty rad. So yeah, I guess I was gonna start by sort of talking about how the company came to be and the history of it. Right now it's just myself doing all the engineering and design work, and my partner Courtney does the graphic design for everything. So I went to school down in Savannah, Georgia at Savannah College of Art and Design, and I was doing like noise boxes and CMOS circuits and sort of really hacky crap down there and selling it to local musicians and other people. And I wanted to make a Eurorack module because I was a Eurorack user at the time. And I didn't really know that much about electronics, to be honest with you. Sort of just going with whatever came along, like very much in the DIY ethos. And I saw, it was like a really weird magical twist of fate, but I saw on Facebook that Lars, who I had followed loosely because of LZX, was moving to Portland to start working at Dark Place Manufacturing. And I was like, I have no idea what Dark Place Manufacturing is, what is this? And I looked at the website and I saw what they were. So I just sent him a completely blind message. I was like, what do you guys do? Like, I have no idea what I'm doing, and I really want to make a Eurorack module because I really like this stuff. And he was like, yeah, sure. Well, I'll just teach you how to make modules. And I was like, really? Like, I don't even know who you are. And he was like, yeah, sure. I'll just teach you everything you need to know about electronics. So everything that I know is from Lars Larson of LZX Industries. And it's pretty insane. I mean, I sent him like a hacked together schematic for G.M.O, which is our first module, which I'm going to talk about. But G.M.O was originally this, it was a Teensy 3.2 and some pots in a hollowed out Bible that I made for my buddy Matt. And it was this weird, like metallic digital noise box thing I made him because I was making him some like analog stuff. I mean, it was CMOS, but you know, typical square wave, bleep, bloop, bleep, bloop, bleep, bloop, crap. And I wanted to do something weird and new, so I made that digital circuit. And then I figured this would be a great place to start. Like, let's take this noise box and let's make it a Eurorack module. So I would draw up schematics, and I was emailing back and forth with Lars, and he was, you know, helping me out and everything. And then eventually, I'd finished school at the time, and I was living with my girlfriend in Savannah. We were just kind of bumming around working. And we just decided to sell all of our crap and drive to Portland. And that's what I did. And I showed up. I worked for Synthrotech for a little bit. Wasn't really my speed. Left Synthrotech, started working at Dark Place, who at the time was, they were still kind of like a client sort of relationship. But I started as a hand assembly technician there, and I learned a bunch of stuff from their awesome employees. Like Thomas Fang works there, who used to work for Bleep Labs, and Lars was there, and Jay has been kicking around Portland, and just all these dudes who've been around for a while. So they showed me a lot of stuff with hand assembly. And to be completely honest with all of you, I'm still, every day of my life, I'm still learning this whole thing. I don't have an engineering background. I'm an art student. And I guess the main message of today's demo, ignoring all of the modules that I'm going to talk about, is that if you really like making synthesizers, and if you really like doing this stuff, you should just do it. And just keep doing it, and you'll make a bunch of mistakes, and you'll make things that suck, and you'll make things that break, and there will be magic smoke. And eventually, one out of every 100 of those things will work, and somebody who knows what they're talking about, you can show it to them, and they'll help you look at it, and you can have your very own synthesizer company. These 3 easy steps. So yeah, that's sort of like, that's the thing that I really want people to understand about all these modules, is the history of it, and the ethos and the aesthetic all comes from that place of me trying to take these broken, effed up, weird ideas, hacky ideas, and put them in a way that's presentable and musical and playable and no menus, no menu diving, no crazy stuff. Like I just want knobs, I want switches, I want jacks, I want single function modules, very straightforward. And I want all the stuff to sound ratty and effed up because that's what I like to do. So the overarching goal for this whole system eventually, right now we're almost at a complete row. Some of these things are now commercially available and some of them will be available in the future, but I want to make a whole drum machine that is like the world's weirdest, most bizarre, crappy, but awesome drum machine. I don't really know what that means yet, and it's still an adventure and I'm still growing, but that's sort of the initial inspiration for everything. So I think it would be appropriate to start with, I'm going to first start by talking about some of the main voices of the system right now. And I'll start with G.M.O. because that was the first module, and I'll talk about the G.M.O. family of modules. Everything's muted right now, Darren, so that's probably just the noise floor that you're hearing if it's cranked way up. So I'll talk about G.M.O. first. So that's this guy right over here. So G.M.O. behind it is a TNC 3.2 dev board, just straight up, slapped on the back of the module. And there's some other circuitry to interface with it, so you can get the Eurorack voltages in and out. But basically, at the core of it, G.M.O. is a 12-bit sample player that's got like 16K sample rate. And it stores about 8 seconds of audio total. So there's a variety of different sound banks you can download on GitHub. I think I have like 50 right now, and some of them are classic drum machines. Some of them are weird, like animal noises, and we have a fart bank, which is fun. There's glass, wood, metal creaks, like all these different things. So it's this weird playback thing. And you have the ability to choose different samples. You have bipolar voltage control over all 4 parameters. You have pitch control. And the thing that's interesting about it that I'll demonstrate is that the pitch control is actually controlling the clock speed. So it's pitch tied to sample resolution. So it's a very interesting sort of sound. And then you also have start and end times for the samples. And you can turn looping on and off, and you can trigger the sound. So I will show you what that sounds like, and then practice. So right now I think this is the RZ1 drum machine. It was one of the 80s PCM drum machines. And you can hear it's super lo-fi, all that kind of stuff. And when you turn looping on, you can get, they're almost like, you can almost do rolls with the looping function, which is nice. So you can do stuff like that, and you can also trigger the loop function. So you can do musical things with that as well. And the loop function will be proportional to the pulse width of the incoming thing. So as you lengthen pulse width, you can do stuff like that, which is pretty fun. And then obviously, you could send control voltage to select different samples. So yeah, it's like a ratchety, glitchy, gross percussion thing. So that's G.M.O. I think I was saying before, I think it's the RZ1. So I took a bunch of, there's that KB6.de, that famous drum sample, freeze drum sample things. So I took all the like PCM drum machines that I liked and slapped those in because I feel like it's sort of, I mean, those are 12-bit machines and this is a 12-bit playback device, so it only seemed fitting and natural. I'm also trying to move away from the XOX 303, 808, 909. Kind of tired of all that stuff. I don't know about you guys, but it's another inspiration is other sounds. So that's where G.M.O. comes from. Now you'll see next to G.M.O. we have these black panels here, which are actually from Magpie Modular. So Chris printed these for me, which is cool, and you can get them from his site. So if you get the G.M.O., in addition to all the other banks that you have, there's also 2 completely different alternate firmwares. So they're totally different modules, but they're free. So you just flash the code to the module, and you get these functions. If you want the faceplates, you can get them from Chris. So the next thing I'm going to talk about is the Mongrel. So the Mongrel started, I wanted, just as like a reference point and just sort of like a weird exercise, I wanted to start with like an 808 cowbell kind of thing. So I just like took a few square waves and I was zoring them together and I was doing all this weird cowbell stuff, and I was like, you know, this is kind of boring. This isn't really what I want to do. This isn't fun. But the inspiration was like stacking a bunch of harmonics up on top of itself and making a sort of additive synth voice for like another metal kind of voice. So what Mongrel is it's actually two sine waves, or two triangle waves actually, fed into a ring modulator and then fed into a decay and envelope circuit. And then you also have the ability to switch between sine and square. So you can get those sort of cowbelly kind of tones. But it's interesting because it's a ring mod drum. And it sort of sounds like a low tom in a weird way. So I'm going to trigger that here. Seems like I'm missing a screw here. That's not very good. So yeah, you have pitch over both of these oscillators here. Let me turn it up. Oscillator 1, oscillator 2, and they're just hard mixed together at the same volume. And then ring modulation between both of them. So you can, again, with modulation, you can get some pretty groovy shit out of it, which I'll show you here, modulating the ring mod amount. Seems to be doing it kind of slowly here. Speed it up a little bit. So you can get these nice like low frequency kind of tom sounds, and then the growl is your ring mod amount, and that's sort of your timbre or color. So the snarl switch goes from sines or triangles, I actually don't remember which one it is, I have to look at the code again, but softer waves to square waves. So that's how you get all that crap. And just like the G.M.O, you can trigger that switch. So you can toggle that function on and off. So, oh, no. So, you can get these cool accents and stuff. Yeah, so that's the Mongrel. Now we're going to move on to Bobcat, which is the third. This is the third voice of the G.M.O family. And what the Bobcat is Bobcat is two channels of decaying noise. So it's like your hi-hats, claps, snares kind of sounds. And the pitch on the Bobcat, there's two channels of it. Pitch on the Bobcat is also tied to a resonant high-pass filter. So it's nice, so as you change the pitch, it also sort of turns crispier and thinner as it goes higher and lower. So it's got two channels of that. Right now I'm just triggering one of the channels. Nope, that's Muskrat. So you can get pretty vanilla kind of stuff. But you'll hear as it gets lower, it gets really crunchy and gross. So here's the three of those together. With the Bobcat, you have CV control over both pitch and decay, which is nice. And then what the snarl switch does is it allows you to change the maximum decay time. So when it's down, I believe it's 0 to 500 milliseconds, and when it's up, it can be as long as 3 seconds. So you can get nice long kind of stuff. So here's short. And here's long. Yeah, so you get the point. Does anyone have any questions about this family of modules? G.M.O, Mongrel, Bobcat? Everybody feel cool about it?
So it's 2 channels that are like pretty much the same thing.
Yes.
Top and bottom?
The Unity gain, yeah. They're with each other.
It's-
Oh, yes, I'm sorry. They're identical.
Oh, okay.
Yes, they're identical channels. So, yeah, the top, you got decay pitch, and they do the exact same thing. And then there's, again, this is the same hardware for all 3. So there's Bipolar Cv over everything. And then you have the trigger for the switch and the trigger for the actual trigger. Which
How complicated is the firmware flashing process?
Not complicated at all. So these are all, almost everything that I do digitally is programmed in Arduino. And in this particular scenario, because it's Teensy, he has an application called the Teensy Loader application. And what it does that's really nice is you can compile everything down into a single hex file. So for firmware updates, it's very similar. It's actually identical to how Variegate 8 works and other Teensy-based modules, where you plug a USB in, you drag a hex file into the loader application, and you just push a button on the back of the module. And that's it. So it's very, very, very simple. You do have to do that, yes. And that was something I was thinking about at the very beginning, but I decided that I just don't want USB jacks on the front. It's like a weird OCD nerd thing. And yes, it's inconvenient. Yes, it has a mini USB jack. No, no programmer, just a micro USB.
So you shouldn't flash them live then?
You can flash them live.
So,
Yeah.
Okay.
I mean, you'd have to pull it out of your case.
Yes. Okay.
It would look a little weird, but
Yeah.
you could do it.
Just leave a USB cable plugged into it.
You could do that too. There's a bunch of different kludgy, hacky ways to do it. I mean, there's also this weird thing that I have. I mean, call me crazy, but I feel like I make the best work when I'm in limited sort of parameters, and I don't like having 50 different things that I could do with a module and 50 different modes and all this stuff. So I like to flash one bank to it, let it hang out, live with it for a while, use it on a few songs, maybe flash it out. I've been using the same bank for like 9 months because it's what I like the sounds of. So get out your pitchforks and your torches and hate me, but that's just what you're getting, man. It's just how it is. So
Is the process of preparing your own samples for the G.M.O complicated?
yeah, it's a huge pain in the ass, but there's a whole tutorial for it online.
Oh, very good.
Yeah, so there's a GitHub for it, and it's kind of a complicated process because this was before I knew anything about the Teensy audio library, which is actually really funny. So I actually work pretty closely with Paul now from Teensy, and I know him, and he's a great dude. And I work with him with the audio library, and I give him updates and ideas and stuff, and get feedback, etc. Because he's not a musician, he's an engineer. Anyway, I thought that the only way I could do this was with the Moffenzeef synthesis library, and I don't know if you guys know that one, but it's pretty weird. I mean, it's written by this guy, Tim Barris, who's awesome, really, really awesome. The library itself is really cool, but it's kind of really confusing to use. And there are some things for the library that are kind of specific to the library, like it doesn't necessarily carry over from Pure Data or Maximus P or anything. So any hiccups that you'd have is like understanding the syntax or like the way in which to write something. But that being said, there's a GitHub for all the digital modules with tutorials and step-by-step process for doing it. It's about, I mean, getting your own sounds in G.M.O, I think is about a 20-minute process, start to finish. Requires a little bit of knowledge of terminal window, a little bit of knowledge of Arduino, and just sort of general programming like, oh no, my code is broken. And it's like, well, actually, you need to put a comma here, you know, like that sort of stuff, which is like 80% of programming, really, just figuring out where the missing comma or the period is. So it's a fun lesson. It's a learning experience. That's the whole goal here. So yeah, that's the G.M.O family, those 3. So that was our first module and the 2 alternate firmwares.
I want to ask a question.
Yeah.
Since you come from an artist background,
Yeah.
so I see there's like different waveforms on the faceplates
Yes.
that represent.
Yes, that was something that I very much cared about. So Courtney designed all of those, but I would sort of tell her and show her on the oscilloscope. Like, it's like, here's what it looks like on the oscilloscope, and like, here's sort of the reduced abstract thing in my head of what I want it to look like, and then she would do it and do a cool thing. So Bobcat is like a super busy, noisy sort of deal here. Mongrel is like a chiller sort of kind of thing. I mean, that's what it sounds like. And G.M.O is kind of just like a generic audio thing because it can be so many different things. But as you go through the progression of the different modules on the ones that it can fit on, I'll talk about some of them later, obviously, but Kricket is these little square wave blips. Muskrat's another noisy thing. Deviant's step voltages for stepped random. Mito is these little cell blob divisions. It's called mitosis, and it's a clock divider, so it's all these little divisions. And then the count is supposed to be like ticks and bars. You can't really see it, but it's like a big blip and then some little one, and that's the master clock module that does global timing. So yeah, it is. I'm glad you actually said something, because that's something that was very important to me in the beginning. And then, yeah, there's also little cute animals and stuff that I'll talk about. I actually didn't even talk about that. Man, that's crazy. So there's a little, you can't really see it, but there's an Ouroboros. I can't even say that word. Ouroboros. It's a, I believe it's Greek for a snake eating its own tail. And it's supposed to be the infinity loop. That's the looping feature. Turn it on and off. I don't know, I thought it was cool. So that's what that one is. But each of these, or some of them rather, have little icons that are sort of specific to the module. So that's the G.M.O. There's a fourth firmware that I've been slowly working on over time, and I haven't released yet, but it's called the Craplust firmware, and that is my janky Carplus Strong. So it's Craplust. That will come out I don't know, it'll come out eventually. But if you have a G.M.O, you can look for it, or you can do your own. But I will say that of any of the platforms in this case that are the most DIY friendly for programming, the G.M.O family is absolutely a great place to start, because it uses the built-in DAC on the Teensy, and you can use Arduino, and you can use Mozzie Synthesis, or you could use the Teensy audio library, which is a lot of really, really powerful stuff. I mean, things like the Orgone accumulator was originally done on that, and I mean, there's just a variety of products that have used Teensy in the audio library. It's really, really solid. It's way higher quality than Mozzie and puts out really clean waveforms. So those are those. I'll move now to my next drum module. So this is the Kricket, and was directly inspired by the famous Nicholas Collins circuit from Handmade Electronic Music. Do you guys know this book? Have you heard of this book? If you're interested in DIY, I highly recommend you buy a copy of this book. It's where a lot of people start, and it's absolutely where I started. Teaches you how to make contact mics, teaches you how to make simple oscillators, utilitarian tools, etc. But Handmade Electronic Music by Nicholas Collins. So the Kricket is inspired by one of the chapters that talks about NAND gates. And it's a common noise circuit that you'll see over and over again. It's basically a square wave that emits a pulse, and another square wave that a square wave that emits a tone, and another square wave that turns the tone on and off. It's pretty simple, right? And I thought to myself, I was like, what if you, instead of plugging a square wave oscillator into that to turn it on and off, I was like, what if you just plugged a trigger directly into it? So it's an extremely, extremely bare bones, simple circuit. But you're essentially, there's 4 pitches, and the incoming gate, the pulse width of the gate, the width of the pulse width is proportional to the length of the incoming note. So at first you're saying, wow, that sounds really lame. That's 4 square waves. Why would I ever want that? But I was working a lot with sort of these like cluster polyrhythm things for a while, where I was using like the SCM from 4MS. And I had like grids for a little while, and I was doing these things where I would have these weird like looping fast repetitive structures. And I realized that those types of things really work best if you have different sounds that share a same timbre palette. So, if I were to use that type of sequencing and say take one trigger and put it into a kick drum, one to a snare, one to a hat, to me personally, for my own aesthetic taste, it sort of felt like this groove that was always falling apart and didn't really work for me. So I wanted to make something inspired by this that I could sort of take my cluster sequencer and trigger a bunch of sounds that sounded really similar. And the result of that was Kricket. So I made all of them really, really high frequency, because I want them to all be these really high frequency chirps, and I want it to sound like a group of crickets. And I put a high pass filter on it so you couldn't hear the thump of the gate opening and closing. And to top it all off, on all 4 of these inputs, there's a super ghetto, if you look at the back of the module, it's really funny looking. There's a huge black like piece of heat shrink on it. And underneath that is this like hairball Vactrol thing that I made. So there's an LED, a 5mm LED soldered directly flush to the PCB, and there's 4 light sensors pointed at the LED. So the incoming CV changes the brightness of the LED, and as the light changes, it changes the resistance of the 4 photo cells, which are in parallel with the pots, which change the frequency of the pots. Now, getting all of that weird science lingo out of my mouth, it makes everything go pew, like a weird like laser sound. So you can get your like cluster rhythm going, and then if you want to accent and make all 4 of them chirp together, you send a trigger into the Vactrol input. And it's actually pretty cool. So I will show you that now. Here's the Kricket. So I'll be going over the sequencer in a little bit, but the sequencer is very much inspired by that same concept of cluster beats. And to demonstrate, I will hook it up to Kricket. Boop. And I call this patch, inspired by an Instagram comment that I saw, I call this patch the Funky Fax Machine. And you will hear why. So at first it's going to start sounding like boring video game music. But when you get all 4 of them going together, they run the master sum a little hot, so you get this cool, crunchy, sort of gross sound. And not to mention the super high frequency signals they can go up to. So I'm going to speed it way up. And I'll get the Vactrol, the Kricket input going. Let me lower the pitch of these. And again, the incoming pulse width is proportional. So as I lengthen the pulse width, all the beeps will get longer. And so on and so on and so on. So I think it's cool. I use it a lot. I really like it. I hope you guys like it too. The other thing that I like to do with it sometimes is like tune it to a chord, you know, do like a root 3, 5, 7 sort of thing, and then you get this like weird funky beep Kricket drum sound thing. So yeah, that's Kricket, and it's not digital, it's CMOS, so there are no firmware updates unfortunately, but yeah, that's Kricket. Now I'm going to talk about the Muskrat. Is anyone familiar, has anyone seen online our other product, the MSG? Does anybody know about that or heard that? So I did this workshop in Portland at the S1 Synth Library. I don't know if you guys know about that either, but it's a nonprofit that's like an educational facility for people to teach them about synthesis. And I did a workshop last year called the MSG, or the Mini Sound Generator. And the whole goal of that workshop was trying to take an AT-Tiny85, which is like a pretty general, cheap AVR microcontroller, and sort of push it to the brink of its functionality. So try to do as much as I could with it sonically before it craps out. So it was this easy to build DIY kit sort of thing. And I made a bunch of different firmware chips that you could swap in and out for it. So there's like phase distortion, frequency modulation, amplitude modulation, granular synthesis, just all these different techniques. And it was really fun, and it was a great hit, and I made some kits, and I made some assembled units, and they're floating around different places. But I said to myself, I was like, you know, why don't I take this idea and sort of take all the best elements of these different firmwares and take all the things that I like from these different firmwares and make one like mega awesome firmware and then make a module out of it. So I didn't want it to just be another noise module, and I'm making drum modules, so I figured, what if I just take the MSG, put it into Eurorack, put a VCA on it, and put a decay envelope on it, and put some CV control over it, and bam, there you go, there's a new module, right? So that's what the Muskrat is. The Muskrat is basically the Eurorack version of the MSG. And the thing that's really cool about the Muskrat is instead of doing everything on the module is SMT on the back, everything's done by a pick-and-place robot. But the only thing I didn't do pick-and-place was the actual AT-Tiny85 itself. And I purposefully made it an 8-pin dip socket. So if you built an MSG, and if you have the MSG expansion chips, you can interchange them between both of the products, which is pretty cool. Or you can flash your own code on an NAT Tiny and pop it right in, which is also fun. So to demonstrate it, first thing I'll show you is actually an Easter egg I found the other day. To make it self-oscillate, if you take any of the CV inputs and patch it in to the trigger input, it'll self-oscillate. Don't ask me why. So, that being said, it's supposed to self-oscillate. It was. Oh, it's in the, that's why. So, just to demonstrate, I'm just demonstrating the oscillator core right now. So, you have, Muskrat is, at its core, it's basically a wavetable oscillator with phase distortion on top of it. So you can kind of, you take these waves and it like pushes the phase and pushes the wave through the phase accumulator and out of the window and just makes it sound terrible in the best possible way. It's sort of like a weird foldy distortion thing. So this, the scratch parameter is the distortion, the phase modulation and distortion. Dig is wavetable selection. I think there's 24 waveforms. And chew is clock speed. So again, it's pitch and resolution. And then last but not least, the Muskrat switch actually does something really cool. When you flip the Muskrat switch on, in the main loop of the code, it generates a random number at the same speed as the master clock is outputting the waveforms. And then it takes that number and it slams it into the waves as they're coming out and just makes everything sound completely fucked up. So you get these weird fringe like sort of things. So that's the oscillator core, and it's got a trigger input. And the other thing that's fun and super DIY and super ghetto, and is sort of in a weird way over time as I'm making more stuff, sort of helping shape the Moffenzeef sound, is my envelope and VCA solution. So it's very much inspired by and taken from the single transistor VCA from the DR110 drum machine. Super garbage, just terrible VCA, general purpose transistor. It's not the correct way to do things. So it's that. And the decay circuit, instead of doing trigger conditioning like most modules do, where you clean up your square wave and you make it this nice, clean, quick pulse, and then you go ahead and follow it and make a nice envelope and everything. It's just like a simple, basically a simple RC low pass filter that's just slewing whatever is coming in. So it's an envelope follower circuit. So the thing that's cool about it, though, that I actually wound up really enjoying about it over time, the more I played with it and used it and decided to keep it, is the fact that you can now feed variable gate lengths into the trigger, so it's not the same exact pulse every single time. And it's also basically just a CV input for the onboard VCA. If you feed CV directly into it, the decay pot becomes a slew amount. And it's just connected to the transistor and is controlling the VCA. So it's sort of like a weird in-between of like you have a CV input or you could just use it as a follower input. So that becomes super useful. I don't have an example of that in my case, but you can do things like you could like take a kick drum track and like split it and put the kick drum into the Muskrat and have it follow the amplitude of the kick drum. So it'll go every time it happens to really bring the house down with that one. But here's what it sounds like when you just patch gates and do it. So the range switch here is actually a 3-position switch that determines the maximum range of that decay. So it's short, medium, long. So now lengthening the pulse width. So that's short. Here's medium. And here's long. I think it's about 6 or 7 seconds of decay time to go all the way to 0. So it's a good option for like weird cymbals and stuff. But I mostly use it personally for really short stuff. I like that sound the best. So yeah, there's some CV inputs here, and those are. This was another weird experiment. So I've been back and forth about how I feel about this. I mean, everyone is just so picky about this topic, but with CV inputs, there's a variety of different ways you can do it, right? You could have an attenuator, you can have an attenuverter, you could have them be an offset, you know. So what I wanted to try with this one, I don't even really know why I did it in the end, but the inputs for them, when you plug CV into it, the pot becomes an attenuator for the incoming CV. So there's no offset anymore. So it's like you're basically controlling the ceiling of the bipolar voltage. So it's a weird thing, because normally when you have a CV input like that, most of the time it's usually like a unipolar voltage, but I'm just like a huge nerd about wanting bipolar CV over everything, because our main modulation source is a bipolar voltage source. And because I like that, like I like the ability to go right and left and right and left. It's just how I think. But the CV on this is, yeah, it's an attenuator for the incoming input. So to show you that, I will turn my sound back on. And I'll plug some CV in. So we got some CV over that, and waveform selection. But if we wanted to do something more musical, we could use the random voltage coming from Deviant. Let's actually use this one, because this one's going at twice the speed. Well, it's supposed to be. There we go. The Muskrat input is ORed together with the switch. So if the switch is down and you send a long trigger to it, you can turn the Muskrat switch on and off. So you can kind of treat that as a weird accent, sort of similar to the snarl switch on Mongrel. That kind of stuff. It's actually pretty musically useful, which is fun. And then, of course, we also have a pitch input. And no, it's not 1 volt per octave. So yeah, that's the Muskrat, and people seem to really dig that one. It's super cheap, which is why I think people like it. It's 130 bucks. And like I said, with the MSG expansion chip, you get like 5 different modules for the low price, et cetera, et cetera. So yeah, that's the Muskrat. I think it's probably a good time to take another break, ask some questions. Anybody have any questions about Muskrat or Kricket, or should I just keep on keeping on? Keep on keeping on? Cool. All right, cool. Sweet. You guys are good. You're doing good. All right, so another really fun one to talk about. The Deviant is something that came from my Max MSP use. So I really, really love random voltages, and I've got a variety of different random voltage generators. I love traditional sample and holds. Turing machine is awesome. There's a lot of different ways to do random. Wogglebug is cool. But not every random voltage generator does the same thing, and they're not all used for the same thing, right? So it's like Wogglebug is awesome for like doing like really crazy unpredictable stuff. Sloth is good for like really low, slow, wiggly changes. Turing machine is awesome for like sequenced music where you're doing that. But something I noticed that was pretty common, a feature that I wanted to see that I hadn't yet seen, was the ability to take a random voltage and instead of just attenuating the top all the way down, which is pretty common, I wanted to be able to scale the range of random, like you can in Max MSP and different random things where you can say, no, I only want it to be random between this range and this range. And that's especially useful in the modular environment where you'll have a patch dialed in and you're like, oh, you know, like I want modulation over this and I want it to be kind of random, but I don't want it to spray all over the place and I really just want to control like this little window of voltages. So that was the whole inspiration for Deviant. So that was how it worked on paper. Now in practice, when I went to do it to sort of keep up with the Moffenzeef ethos of what I call craptastique electronics, musique craptastique, instead of using a DAC, to make it weird, I just took raw PWM voltages off of the chip and I put an RC low pass filter on it. It's also known as the poor man's DAC. It's really interesting in terms of how it sounds in the modular environment. So that's what this smooth knob is here, because I was doing different experiments and I was like, well, you know, like I like that it's kind of wiggly and woggly and bouncing all over the place, but like at the same time I want to be able to control that and dial it back. So the smooth knob, it's not just slew amount, it's also removing that noise slowly, not entirely, but slowly removes the noise as you turn it up. So with smooth all the way down, if you were to plug Deviant into an oscillator, you'll hear that it gives it this sort of weird FM quality to the sound. So here's a very clean oscillator, Morphing Terrarium, awesome design. And listen to how the Deviant makes it sound really bad. All those weird ringing and sidebands. And as we slowly turn up the slew amount, you can hear it kind of goes away and it becomes a little wigglier. So it goes all the way -5 to 5. If bottom is all the way down and top is all the way right, it's full range random. But it's a window of voltages, so you can get everything in between. So you could say, give me just negative voltages, make it only go downwards in pitch. Or you can slowly raise that window. Or you can go super high. And everything in between. So, you know, I did the noise thing at first and I was like, I don't know, it's kind of weird. And then I started using it with a bunch of modules that are out there and modules that are in my case and modules that I make. And I realized that that sideband noise from the PWM is actually totally useful if you like glitch stuff. Because what happens is on modules that are either quantizing things like a quantizer, where they're trying to lock pitches down, or on something that is expecting a stepped input, like a sample selection on radio music, or like any kind of like, there's like 32 things on this knob or whatever. It's really cool because what happens is you land on a value, but because of the noise in the signal, you get all these like Rice Krispies on either side of it. And I was like, man, I don't know. And the more I played with it, the more I was like, you know what? I actually really like that, and I'm going to keep it, and I think it's cool. So that's why I didn't do a DAC, and that's why I didn't do filtering, and that's why I didn't try to clean it up. It's because on things like G.M.O, which you'll hear in a second, you can make it sound even more effed up than it already is. So we're going to control sample selection with Deviant, and listen to how it'll choose a sample, and then it'll it cries. All those. Let's speed up this random voltage here. Oh, why is that plugged in there? It's stupid. Let's do this. Yeah, so it's all those like Bob Ross happy accidents happening in between. Which is what, this is basically the modular version of a Bob Ross painting, only it's way less beautiful and much more barbaric. So Deviant also, the other thing that's nice about it is channel 1, the trigger input's normalized to channel 2, which is pretty cool. So you get 2 random voltages from one trigger source. So something that I like to do a lot is like, you'll have this one, I'll be showing that in a second when I get to Mito eventually, but actually that's not how I use that at all. But anyway, I'll have one channel of the Deviant controlling, it's like a macro for all the musical skeletal structure changes of the patch. Then the other channel of the Deviant I use for controlling timbre throughout the patch. So for me, it's like the Deviant is sort of the macro control hub for the system. But it also has, I actually didn't mention that, other than normalizing these top and bottom CV jacks, another fun feature about it is that it has bipolar CV control of both the top and the bottom. So that's kind of weird at first because you think like, oh, well, what happens when top crosses bottom and bottom crosses top? But what you can do is things like create a window of voltages like this, and then sort of like take the window of random and like make them go all the way up to positive voltages and then make them go all the way down to negative voltages, which is pretty cool. So again, if I go to something like the morphing terrarium here, and I control pitch and get it pretty close to 0, and then feed it a slow-moving CV into the top jack, what will happen is they're both at like around 0 volts, but the top window is going to slowly start moving upwards. So it's going to slowly start opening up and feeding only unipolar positive voltages. And then as it comes back down, you'll see that plus sign slowly dim until it gets back to 0. If I speed this up a little bit. So you can see the random range gets bigger and smaller. Same thing goes for if we were to feed it into the bottom and do negative voltages. Same exact story. And you can do all these different things in between and get all these different random results, which is fun. And also, if you wanted to, you could patch it back into itself so you can get really weird random sounds. So that's Deviant. That's annoying. That's Deviant. Now, I will discuss Mito. So this just recently came out. And Mito is like, it's like a few of my favorite different modules sort of all strung together. And honestly, it was very much inspired by the shuffling clock multiplier from 4MS, which is like, everyone in this room should go out and buy that module right now because it's like the coolest. That module, I mean, like 2 of the things in this case, I've already mentioned it once. Like Kricket and Mito both came from inspiration from that module. So what Mito is, it's a little different, but basically it's a 6-channel clock divider, and it's like a polyrhythmic drum machine, basically. So it's a 6-channel clock divider, and each of these knobs specify the clock division all the way from 16, divide by 16, all the way up to divide by 1. Each channel has its own mute switch, so you can turn parts on and off musically. It has global swing, which is the amoeba knob, so it gives it like a little wiggle. That's why it's called the amoeba knob. And it has global pulse width here. And again, everything has bipolar CV. So, because it's a division-based sequencer, for most musical applications, you'll want a pretty fast clock. Because if you think about that logically, you need a bunch of pulses first, and then you have to slowly divide down from that to get musical results. So that's also why the count was created, which I'll talk about next. But basically understand that the count is like a super controllable, very fast clock module that also has other features. But count was made for Mito, Mito was made for Kricket, Mito is controlled by Deviant, etc., etc., etc. Moffenzeef family. So I wanted Mito to be this polyrhythmic sequencer that was like sort of like when you pair it with the Deviant, this like mini cluster of modules becomes this pseudo-random, still controllable, like generative polyrhythmic drum machine thing. So if you want a 16-step sequencer and you want like total control over your drums, don't get Mito at all. If you want a really weird, experimental, fun, just different way of approaching sequencing, then this might be a good fit for you. Yeah, so without further ado, I will show you how it works. So I'll start by triggering Muskrat with the first channel here. And the reason I laid it out this way was because it made the most sense for performing. So divide by 16 is all the way left, and divide by 1 is all the way right. And the reason why is because when you play with it, you associate that knob. The reason why nothing's labeled is because I don't want people to get like all caught up in like, oh, is this actually divide by 5 or is this divide by 4? I'm going to write you a really angry email about it. You know? So I want it to be like complexity of rhythm. That's what I wanted to think of. And I don't want people to think of it as a generic utilitarian clock divider because it's not really what it is to me. It's this other thing. So as you turn the knob to the left, you can see the light blinks less. And as you turn the knob to the right, the light blinks more. So it becomes either more complex or less complex. And if you turn the knobs up and down, you make cool music. So that's what I'm going to do. Here we go. So I'm going to speed up the clock. So with one channel isolated, it's not really making any music because you can't hear any of the other musical references. But you do see what the function of the knob is, right? As we turn amoeba up, listen to what happens to the 16th notes. They start to swing. Get up. Yeah, let me slow it down a little bit. You can hear it much better at slower tempos. It's like a horse galloping, and this is like a robot galloping, right? Swing and pulse width. So at the root of it, it's extremely simple and straightforward. But it really gets fun when you start to patch a bunch of different stuff and you start to modulate it. So that's what I'm going to do. I'm going to start with Muskrat, and then I'm going to do some Krickets. And then why the hell not? Let's do some G.M.O. Okay, so what I'm going to do, and actually this is going to be like a sort of segue into the count, but the count here, before I go into a bunch of detail about what the count does, it's master clock and it's got a bunch of divided outputs. So I'm going to take the divide by 8 output, and I'm going to clock the deviant with that. And the reason why is because I want that to be thought of as musical bars, basically. So every bar, I want a random change to happen. And I want to take that random change, and I want to control all of my rhythmic elements with it. Pretty straightforward. So I'm going to take that random voltage, patch it into bus mult, which I will also go over in a little bit. And I'll leave one of my channels at a fixed clock as sort of the musical reference of like, okay, this is where the beat's laying. And then I'll let everything else shuffle around that. So I will take the 4 Kricket channels, which are channels 2, channel 3, channel 4, and channel 5, and I will modulate all of those with the deviant. And what you'll notice will happen is, because these pots become offsets on this module here, the deviant, if you look at it here, is basically controlling where left or right these pots go. So if you have the top all the way to the right, it's going to turn the knob all the way to the right, and it's going to be divide by 1, the most complex. All the way left, it's going to be the least complex. So here's what that sounds like. So let's get G.M.O. on a more steady 4s, right? And now we're going to take our Krickets and we're going to modulate them, and we're going to speed our clock up. There we go. So you'll notice as I start playing with Deviant, it's sort of the macro control for these generative structures, right? So if I turn top all the way up, it's going to almost always go to the right and do that divide by 1 thing. If I lower it, it's different. So you can see right now that some of these are kind of doing the same pattern. I can adjust the offset of them like this. Let's turn the swing up. And I'm going to slow it down a little bit, and you'll hear it'll get really funky when I do that. Now I'll start modulating the G.M.O. with that same random voltage. And so on and so forth. So yeah, there's these different mute switches, so you can turn these patterns on and off, which is fun. And you can control, you can also control swing and pulse width with Bipolar Cv in the same way. So,
Are fractional divisions possible?
sorry?
Are fractional block divisions possible?
Well, they're all, it's 1 through 16. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, et cetera, et cetera. So you can get odd divisions, but fractional, not quite. One thing that,
Like continuous modulation of division.
yeah, you can do that.
Yeah.
Yeah, yeah. Are you asking if it's quantized? Like if the...
Yes.
Yeah, so Mito updates per step, which is pretty cool. So it works in a similar way to like an analog clock divider. So, you know, different digital ones use averaging and stuff, but this works per step. So
Oh,
if,
that's very
yeah, so it'll
So you can throw a sloppy clock into it and it'll follow it.
well, a clock not so much because that's going to go from 0 to 5, you
Yeah.
know? Like it'll just keep turning right. But you could feed it a slow moving arrhythmic modulation and it'll still kind of sound quantized, which I'll show you here. So this is in the Muskrat channel here. And as this gets faster and rises, oh wait, it's the wrong channel. Here we go. So channel 1. So it's arrhythmic. It's just a random CV, but because the calculation is happening per step, it's always going to be musical and quantized. Because it's just a hard division from the last thing. So does that answer your question? Yeah, cool. Sweet. Yeah, so that was something that was very important to me because as I was doing experiments with this, I noticed that if you do things like clock multiplication and averaging, when you do different weird modulation stuff like this, sometimes it doesn't quite work the way you think it's going to or work in the way that in your head you think it will. When you do things per step like this, like the same way like a CMOS shift register, a CMOS counter, or something like that, it'll kind of always be forced to be musical because it's waiting for the next pulse to do the next thing. It's not doing anything between pulse A and pulse B. So, good question. And it also has a reset input, which holds, oh, actually the cool thing about the reset input, which is different from how a lot of stuff works, some of you may like this, some of you may not like it, but I actually really like it. It holds everything high as long as the reset pin is high, which is kind of a different way to do reset. So your reset is also going to be proportional by pulse width, but you can also hold reset down and everything will hold on divide by 1. It'll just over and over and over again. So as long as reset's high, it's just going to keep resetting. So it's not pulse based. You know, you can whenever you want, you can throw reset on, and it's going to reset based on the incoming clock. But it stays high as long as it's high. So yeah. So now I will talk about the count. So the count is my idealized clock module, which sounds silly. Why would someone make a clock module at this point in time in Eurorack history? But what I found in my experiments and my playing was that I couldn't really find either a square wave LFO or some sort of clock module that had the right range that I wanted. That sounds like such an arbitrary thing, but I don't know how many of you have used a square wave LFO as a clock. It's so weird. Like some of them are like, oh yeah, like this is really what I want. And you're like, oh, I touched it very slightly and now I'm 20 BPM faster. Or it's, oh yeah, it's really great here and then it gets really fast, you know, or just like weird ranges like that. So
Maybe you're using the wrong LFO.
yeah, well, maybe I am using the wrong LFO. Maybe I am. I wonder who makes one that might serve a better purpose. So for this module, it's got a range switch. So with the range switch down, it's like super, super, super duper slow. May not be the most useful for drum stuff, but maybe if you make weird ambient music and you want weird event changes to happen over very long periods of time. In this range, with the right clock settings set for the divisions, the slowest possible cycle is once every 9 minutes. I have yet to find a use for that, but it does that. So in the slowest range, that's what that does. This is the overall range of everything. In the top range, it's sort of the more quote-unquote musical, faster pulses. So you got a big, fat Selco coarse knob. Let me actually do that. So you get a big, chunky Selco coarse knob for your fancy schmancy coarse tempo changes so you can feel like a cool all-star DJ. And you get your fine tune here, the little baby one. That I think is like plus or minus like 10 milliseconds. It's like a nice narrow range. And then you have Bipolar Cv for your master clock. You have control over global pulse width for all outputs. Something about the pulse width that I wanted to do, and it's the same with Mito, is the pulse width actually only goes to 50%. And instead of going all the way to 100%, I was playing with that and I realized that there's really not any scenario for myself where I want the pulse width to be longer than 50%. I found that it would kind of just hold too long and wouldn't do the things that I want it to do. So it tops off at 50%. If there's anything about either of these modules in terms of divisions or ranges or whatever, you can open the Arduino sketch and change a number. It's free to do. It's open source. It's pretty fun. And I answer my emails. So if you have questions, I will answer. It's very rare, actually. So yeah, so you got global pulse width. You have a start-stop switch. Now, fun thing about the start-stop switch, Ben Davis, a good friend of mine, who made this thing, maybe some of you have heard about the Varigate 8. Ben Davis, genius wizard programmer guy, made this. He said, hey man, when you do the start-stop switch, instead of having a reset input for your divisions, why don't you just have it send one pulse when you flip the start switch? I was like, oh my God, that makes so much sense. Because now what you can do is when you hit start on your master clock module, you take that one pulse and you plug it into all your resets on everything. And you never have to worry ever again about, oh, is this resetting at the right time? Is this the right pulse width? Oh, like this whole crazy weird thing. So this is the head of the chain clock here. So there's no clock inputs on this at all. This is just the head of the chain. So there's CV inputs. There's bipolar CV over master speed and pulse width. But this is meant to be your number one clock. Everything else comes down from there. So that's what start-stop does. Beat up, down changes from upbeats to downbeats on the divided outputs. So these 4 outputs here are the divided outputs. You can't really see it on this diagram, but there's these like Da Vinci Code numbers all around the jacks. And they're not a cryptic weird message. They are the divisions of the outputs. So these 2 switches here, they say top, bottom, left, and right. And what they correspond to is there's these 4 numbers around. So really the best way to think about it, instead of calling them top, bottom, left, and right from your perspective where you can't see the actual numbers, You can think of top and bottom as evens and odds. So when it's in bottom, the 4 divided outputs are 2, 4, 6, and 8. And when it's in top, they're 3, 5, 7, and 9, right? Your evens and your odds. And you can think of left and right as really a divide by 4 output. So when you flip it left and right, it's sort of going between bars and beats. It divides all the outputs by 4. So I can show you what that sounds like. And your main output is what's coming out of your master clock, which is your really, really fast output. So here we have the 4 pulses of the apocalypse. So this is divide by 2, 4, 6, 8. Here's divide by 3, 5, 7, 9. And here's divide by 4. So although you could trigger stuff with this, the design was focused on being your macro controller. So how I want people to use this, and you don't have to, obviously, but the way I want people to use it is you feed the fast clock into Mito, so you have your really, really, really fast clock to work with, and you can go really, really, really fast with it, and it'll give you good, like, ratcheting territory. Like, if that's your divide by 1, then everything around it, it's almost like a multiply in a weird way if you start with the fastest possible pulse, et cetera, et cetera. And then I want people to take the divide by 4 and plug that into Deviant. And now you have a macro. And you can use all your other outputs for different stuff. But the other day, I had the count, and I had a key step, and I had Mito, and I had variegate, and they were all running off the count, and it was cool. It was fun. So that's why I made that. So that covers almost everything in terms of what is currently commercially available. So that being said, I can take another quick moment to answer some questions before I talk about new prototypes that are coming out in a minute. Anybody?
The Deviant, how fast will it take it? Will it operate up into audio?
It won't go to audio range, but it'll go to really effed up warbly range, if you'd like to hear that.
Yeah.
It sounds like this. I believe that's the fastest it can go. Like that. Any other questions? No? Okay, cool. Actually, before, I have one last thing to show you. This is the really cute thing. This is the Christmas gift that all of you will buy your nieces and nephews. This is the Mageddon. So what this is a little noise kit. You can get a DIY kit, or you can buy it assembled. And I might be able to prop it open. The battery's probably a little snug, but it's super, super simple to assemble. And it's the same chip as the MSG. It's just a single computer chip. It's like 5 components. But it's basically this like super crazy... Oh, I'm stuck in there. Yeah, it's really in there. Look at that. Well, we'll just go ahead and force that in there. There we go. That's great. So, it sounds like this. This was another workshop I did at S1. Crazy glitch synth. And it has a CV input, just a unipolar CV input. So when you feed it really slow modulations, it like you can hear the stepping in the ADC, which is really fun. That's just a slow-moving LFO turning the knob. And as you do it faster, it'll sound more like white noise. etc., etc. I also have a mod that I posted on the GitHub that you can hack this and you can make it a unipolar random voltage generator for stuff like the Basel Castle or any of that other cool desktop stuff. It'll output a 0 to 5 volt random based on the rate, which is the pot. So it controls the overall speed of that. So this is actually a great segue into the next thing I'm working on putting into production right now. I don't have a due date yet, but I know that the rough price range for this is going to be around the same as the Muskrat. It's going to be 130-ish. And this is probably the most fun I've ever had making something and the thing I'm most excited about. But it's our new 4 HP drum called Dialup. And it's basically the Eurorack version of Mageddon with some different code and some different features. But people kept saying with Mageddon, they were like, man, that sounds like a dial-up modem. And I was like, what if I really, really actually tried to make something sound like a dial-up modem? So that's what Dialup is. And it's a line of code, just like Mageddon. It's a line of code that doesn't really make any sense. It's inspired by, has anyone heard about Bytebeat? You guys know about that stuff? By Viznut? That was like the internet thing of a few years ago. So both of these devices were actually inspired by Bytebeat. And what Bytebeat is, you're basically taking an algorithm and through like data mashing and bending through like weird algorithms, you're making a PCM audio line just glitch out and do crazy stuff. The reason it's called Bytebeat is because you can get these certain chains of algorithms, if you guys Google it and look it up, that will create these looping rhythmic structures, which are really cool, and it'll sound like 8-bit hardcore dance music. It's like really weird. So it was very much inspired by Bytebeat, but instead of trying to get a beat, I wanted to create an algorithm that you could control with a pot that just creates just spaz noises. So with Dialup, it was you'd be surprised at how difficult it was to get this thing to sound like a dial-up modem. Like you'd think that would be a really simple thing, but I've spent like 2.5 weeks in my underwear in my living room staring at this line of code, just slopping around different numbers until I could get it to sound like this. And this is the result. So right now I'm just going to feed an offset into it so you guys can hear the algorithm. So that's the one right there. Yeah, so that's the oscillator core. And you have Bipolar Cv Control over that. So it's kind of tied to pitch. It's also controlling the clock speed, so it gives you the illusion of pitch, but it's kind of also just slugging around some numbers inside a line of code. So here's what it sounds like with the trigger in it, what it was originally intended for, is drums. And with longer envelope times, you'll get all that crap. So it's something like Deviant. Let's actually do something like this. All right, I'll spare you guys. So that was Dialup. Next, this we actually did another S1 workshop on this, the bus molt. These are, anytime you see, in the future, by the way, this is like secret Moffenzeef code, but anytime you see a laser cut black panel, that means it's next in the queue for prototype. So everything in here that's a plastic panel is coming up soon. So, bus molt. Every system needs a molt, and I was trying to think of how I could do a molt in a way that's slightly different. So, it's 2 HP molt with a pretty typical normalization scheme where you have the first group of channels normalize into the second. But what I did is on the back of each molt, there's two 2-pin headers. So what you can do, they're connected to the end of the bus of the molt. So what that means is this normalizes all the way down here, and then the last jack over here is connected to that 2-pin header. So what you can do is with these little jumper cables, you can daisy chain all the passive molts together in your system all the way down, and you can plug something into the top, at the top jack here, and it'll go through all your other molts without patching it at all. And then because it's normalized like that with the switching, any point in the chain where you break that molt, that will also carry down into the molt, as long as it's the last thing that happened. So for instance, to show you, if we were to patch Deviant again, quickly, into bus molt, and then we'll patch Morphing Terrarium to the output. You'll see I can get the signal here. I can get the signal here. But then it also, if you follow the arrow, it goes down and then in to the next one. So I can also get the signal here and all the way down here. Or I can break that chain and plug maths in instead in here. And now it's taking maths here, normaling down, etc., etc. And the thing that's nice about it is it's just like a Super Mario pipe. You can just keep going and going and going and going and going, and it'll just keep normalizing down. And they're passive, so they don't draw any current. So yes, there will be a slight voltage drop, but whatever. That's an internet argument that I don't feel like having. Man, it's nice to see you guys in real life. That's bus molt. And I think what we're doing, we're talking about it now, trying to make it make sense, but I think what we're going to do is we're going to do it in packs of 3. So you get 3 at a time and 3 cables. And don't quote me on the final price, but I'm pretty sure we can pull that off for a little under $100, which is pretty rad. So that's what we're working on with bus molt. And last but not least, this is still under development, not quite at the finish line yet. I'm still got to spend some more time with it. But here is the muffin mix, or muffin mix, if you actually read it with the stupid O. So what muffin mix is it's a 4-channel audio mixer. And it's something that I have always wanted in a drum skiff, because I have a variety of different drum modules from different manufacturers, and for different reasons, certain modules are quieter or louder than others. For some reasons, there's a design constraint, and they want to keep it within a given headroom so it doesn't clip at a DAC, or maybe something's super hot, whatever. But something that was very important to me was variable gain in different ranges. So there's different performance mixers out there right now that do stereo and panning and all this different stuff. All of my music is slammed through a distortion pedal in mono. So I just want like full throttle gain in a mono small package. So if you like ratty sounding drum stuff and you want a screaming mix, this is your ticket right here. So that being said, each channel is outfitted with a gain pot that you'd find on any typical mixer. But for each channel, there's an LMH, low, medium, high switch. So that changes the maximum gain setting. So what that means is all the way down, it's ×2. So that will allow you to get just a mild boost if you need just like a little bit, or a nice mild crunch on an oscillator. The middle section is ×5. So that'll be enough to bring up most line level sources to modular. It'll also still boost quiet stuff, and it'll give you like a medium crunch. And then high is 100 times gain, which completely blows the shit out of anything you plug into it and makes it scream at the top of its lungs. Now, at the bottom here, we have these 4 mute switches. And I'm trying really, really hard to get the noise floor as low as I can. I noticed today when we were listening to it, there's still a little bit of bleed, and that's kind of really bugging me, and I'm really trying to narrow that down if I can. But it's a goal of mine to be able to have a really high gain circuit and high gain stuff that you can, from the high gain, be able to dial the volume down so you can actually mix it and actually mute it without hearing it when it's muted, which sounds simple, but it's kind of hard. So I'm like working on that now to get that mute super quiet, and hopefully I can pull that off before it ships. So those are the overall features of it. I can show you what it sounds like. One final thing is this link input here. It's similar to the aux in on make noise stuff. It's a unity gain input that is matched to the master output of the mixer. So the idea behind that is if you had multiple muffin mixes, you could daisy chain them all together and they would all be one big mixer. Or you could take another mixer, like a passive mixer, and plug it into there and daisy chain them together.
Will that be enough gain to get like a contact microphone system up to modular level?
Yes, absolutely, yeah. Yeah. You would definitely be able to do that with
Or
this.
guitar?
I haven't tried that yet, actually, but I'd imagine with 100X it's totally doable. That's a good question. You got good questions tonight. Those are good. So Phonogene's a great example because on some of the samples in Phonogene, sometimes when you do the cool, crispy, fast, granular stuff, you need some makeup gain on the output. And not only that, if you're like me, you want a lot of makeup gain on the output. But I'll start with just the quiet sort of unity gain stuff. And I don't even know if there's a sample in here right now. There might not even be a sample in here. Let's see. Oh, I should probably turn the mute switch off. That would help. Cool, so this is from the project I was working on this afternoon, and this is actually a great example because I have this really cool thing that I love, but I recorded it with too quiet of an input volume, so now I'm going to boost the gain in post. So here's 5x. That would sort of be like a cleaner boost, and then 100x. But this would probably be a better example with like a modular kick drum kind of thing. So let's do that actually. So I'm going to patch up like a pretty generic kick drum. Hopefully the morphing terrarium will give me the snap that I want. So if you'll bear with me for just a quick second. I want to patch this into here. Then I want to patch this into here. Oh my god, terrible. And then I want this in here. So all right, so this is actually a good example. So here we go. So here's like quiet gain. Let me actually turn this up a little bit. There we go. That's what I want. All right, so you have like a clean kick. This is the first gain stage. This is all the way left. You can hear how much gain it is. It's like a mild crunch. You get that nice tappy click sound as it's clipping. Now we'll do the medium gain stage. Starting to get more of that gabber. And now full throttle. So in a practical application, let's trigger Muskrat, which is a little bit on the quieter side. So yeah, that's what it does. And it's got pretty blinking lights. Woo. And then you can mute. So the mutes are pretty damn quiet, but yeah, it's actually still pretty damn quiet. I don't know. I was hearing it before. I'm going to work on this really hard until it gets to your door, I promise. But that's what it does. That's the muffin mix. So that's pretty much all I brought for you guys today. I could blabber on about some other secret stuff that I have coming up if you're interested, but I don't have any visual representation of it, so it would be complete vaporware at this point in time. And as far as you're concerned, that could be a unicorn module. So I am making a standalone drone synth, though, so that's what I'm talking about. And if you follow us on Instagram, you can see some stuff on that there. It's called the Stargazer. I'm only making 25 for this first run, so it's going to be a super small batch, and anyone who owns one is going to be way cool. So if you're one of those people, you'll be really cool. And if you're not, you'll not be cool. So that's how that's going to go. So Stargazer's coming out soon, and it's basically, it's a wavetable, it's a drone synth that actually doesn't have any CV or MIDI functionality at all, because I want it to be a drone synth and nothing more, nothing less. So it's a wavetable oscillator core with 98 wavetables, and they're all really pristine and clean, actually. This is a very rare occurrence for a Moffenzeef product, but very clean wavetables, 98 wavetables. You have a second oscillator that can detune or be put in a sub-octave. It has a resonant filter. Resonant filter goes into a bit reducer and a sample rate reducer, then a second resonant filter, and then after all of that, it goes into a CMOS distortion circuit and then out. And the icing on the cake is there's 3 independent LFO sections where you can select different waveforms to control the resonant filter 1, resonant filter 2, and a VCA before it hits the output. So imagine what that looks like. And you'll see it eventually. But I don't have it with me. And the enclosure didn't fit, the PCB didn't fit in the enclosure. I was going to bring it, but it didn't fit, and we're still working on it. So that's all I got. So yeah, I am Ross. For those of you who didn't hear me at the beginning, I will be standing here immediately after the applause, and I can answer any questions. I bid you adieu. Thank you.